Good morning, class. Today we're going to do a couple more examples using some connected masses. These ones are going to be a little trickier. Let's look at our first example. A 1,000 kilogram elevator has a 1,200 kilogram counterweight, and if a 75 kilogram person stepped into the elevator, what force will the motor, because elevators are attached to motors, have to exert to raise the elevator at a constant velocity? Well, that's a bit of an odd one, but let's take a look. Elevators are kind of made like this. This is my elevator box. There's a cable that comes up and it wraps around a motor. And then it'll come over to a counterweight. And inside this elevator, there was a person who stepped in. Now we know that this counterweight has 1,200 kilograms of mass. How much mass in total is in this elevator? Well, we got the 1,000 from the elevator, but we also have the 75 from the person. We can just combine them and put them together. Now we need to know how much force does this motor have to use. Does the motor have to pull up? Does the motor have to push it down? Who knows? Well, for us to figure this out, we need to write in all the forces that we know to do this. So let's make our free body diagram. We got our force of gravity. I'm going to call it force of gravity E for force of gravity of the elevator. And we have the force of gravity of our counterweight. Now that still hasn't told me which direction I need to put this motor. That's unfortunate. Let's see what the rest of the problem says and see if this gives us any hints. We're asking, what force will the motor have to exert to raise the elevator at a constant velocity? So we know that the elevator needs to be pulled upward at a constant velocity. Oh, that's the key here. Constant velocity tells me that my forces must balance, or it will tell me that my acceleration is equal to 0. So let's take a moment and grab our calculators and actually see how big are these forces that we have. 1075 times 9.8. Our elevator is exerting 10,535 newtons. And let's do the same for our counterweight. We see that's 11,760. It looks like our counterweight is winning because it has a larger force. But that term, constant velocity, told us our forces must balance. The motor up here at the top is going to have to work to help in the elevator's direction. The motor is going to have to pull that way because the force of gravity of elevator isn't big enough to actually balance the force of the counterweight. It's like the motor is actually pushing the elevator down. You could also view it as the motor is pulling on the counterweight. It's pulling the counterweight up to help balance it. So now that we've determined which direction the motor is pulling, by reading our question closely, we can make a net force equation. I said that the counterweight is in the winning direction and the motor is pulling against it. And the gravity from the elevator is also in the opposite direction. Now I want my net force to be 0 because that's the only situation which is where we have balanced forces. And we can see here that this ends up with the force of the motor being 1,225 newtons, and we see the direction given on our free body diagram. Okay, let's try our next problem. Two blocks are attached by a rope as seen in our diagram. The system is accelerating at 0.7 meters per second squared. Determine the mass of the hanging block. Oh goodness. This block here, I'm going to call it block A, we don't know its mass. So to determine that mass, well, we're going to have to use our net forces again, which means we need to make a free body diagram. Gravity is going to be pulling this guy down. This 5 kilogram block also has some gravity pulling it down, but onto the table. I'll call this one B. Now there aren't any other outside forces on mass A. There's no friction, and the tension is an inside force, so I'm not going to draw it in. But for outside forces on mass B, we also see that there's some normal force, and there's also some friction, because that's what that coefficient of friction there is implying. Now we see the acceleration is going 0.7. What's going to happen to the direction of that acceleration as it gets to that pulley? Well, it bends down like that. So to the left and down is our positive or winning direction, and to the right and up is our negative or losing direction. And if we highlighted the directions of motion, it'd be like that. So this is what tells me which forces I should include in my net force equation. That's all good, but there's an issue. I don't know my net force as a number, I don't know my gravity of A as a number, and I don't know my force of friction of B as a number. This is going to be a little tricky. Well, let's see what we can do to find the force of friction of B, at least. Because at least with B, we know the information, like how much mass it has. If it is 5 kilograms, 5 times 9.8 is 49 newtons, so we can solve for its gravity. We see that the normal force is currently being balanced by gravity, so it's 49 newtons. And we'd be able to use our formula, the coefficient of friction times the normal force is going to make our friction. So that's 0.45 times 49. So now we found the force of friction. I can input this straight into my formula, 22.05. This is where we need to get comfortable with using formulas inside our equations. Force of gravity is always figured out by taking the mass and multiplying by 9.8. So mass A times 9.8 comes from force of gravity A, because that would be how I solve it. The net force is going to be our mass times our acceleration. The acceleration is 0.7, but the mass has to be the mass of all the things that are being pulled. It's the mass of A, which we don't know, and the mass of B, which we do know, is 5. When we look at this, the variable is in two locations, but it's the same variable. We actually can solve this now. Let's go ahead and use a little bit of distributive property and try to figure this out. So we get 0.7 mass A plus 3.5 equals 9.8 mass A minus 22.05. Now what we have to do here is be very careful in our algebra. You must combine like terms. So anything that is attached to a mass A can add or subtract to each other. Things that don't have a mass A will be able to add and subtract each other. Do not mix them though, because that's not something that we are allowed to do using proper algebra. Everyone, make sure to really review your algebra if you do not understand how that works. So, I'm taking a look here at mass A. I don't want mass A on both sides. So what I'm going to do is I'm going to take a moment to subtract 0.7 mass A's from both sides. From that side of the equal sign and from this side of the equal sign. And I will only do it to like terms. So that cancels out, and we see here that I have left with 9.1 mass A. I'm also going to do the same function with the numbers. Instead of having negative 2205 on this side, I'm going to add 22.05 to this side. But what I do to one side, I have to do to the other, 22.05. And as you can see, I've lined them up under their like terms. So cancels that, and here I'm going to get 25.55. That's going to equal my 9.1 mass A. Divide both sides by 9.1 to get mass A all on its own. And go ahead and use your calculator. 2.81 kilograms. Taking a look at this problem, what's different about this problem? We still have our net forces, we still have our free body diagram. What's different is when we made our first level of our net force, we need to break down our individual forces into their formulas. Force of gravity A turned into 9.8 times mass A, and the net force, we see mass times acceleration, we can actually write the mass as mass A plus 5. When you're left with one variable, even though it's in multiple places, you can algebraically solve. That's what makes this problem a little trickier. I hope you get it. Let me know if you have any questions.